So in section 13.5, we're going to talk about the ideal gas law. We've talked about 3 different gas laws relating volume to temperature, volume to moles of gas, and volume to pressure. Yeah, that's what that is. That's a P. That's a pressure. We can put all of those together into one law that's called the ideal gas law. And that's PV equals nRT. Some people call it PIVNERT. You know, there's no vowels in there, so it's kind of hard to pronounce. PIVNERT. So this is a very useful equation. Now, we've talked about P, V, N, and T. There's a new letter in there. It's a capital R. And that is called the universal gas constant. And its value is 0.08206. And it's got some kind of wacky units. Liter atmospheres per mole Kelvin. Where do those crazy units come from? Well, if we take the ideal gas law and rearrange it to solve for R, that's too fat. Come on, there we go. R equals, still looks kind of fat. It's okay. R equals PV over NT. What are the units on volume? Liters. And pressure in atmospheres. And N is moles. And temperature is Kelvin. Liter atmospheres per mole Kelvin. That's where the crazy units come from. When we did those other gas laws, we had to make sure that the temperature was in Kelvin, but the other ones didn't matter so much as long as they canceled out. When we're using the ideal gas law, we only have one set of conditions, and so the other units aren't going to cancel out except for with the ideal gas constant, or the universal gas constant, whatever you want to call it. So we have to make sure that our pressure is in liters, our volume is, pressure in atmospheres, volume is in liters, N is always in moles, and T is always in Kelvin. So let's do some examples with this one. So an automobile tire at 23 degrees Celsius with an internal volume of 25.0 liters is filled with air to a total pressure of 3.18 atmospheres. Determine the number of moles of air in the tire. So we read this question or this problem. It's not really a question. There's no question mark. And you may or may not recognize that this is an ideal gas calculation with the ideal gas law, not one of those other ones, because we don't have changing conditions. Let's assume that we don't recognize that we're just struggling with deciphering these stupid word problems. So what did we do with the other ones? We made a table, right? So we can make a table for this. We'll find out that we didn't need it, but it won't hurt. It won't hurt to make a table. So let's make a table. So we come to our first here, we're making our table. We had 1s and 2s. First set of conditions, second set of conditions. Then we put the numbers in there. So 23 degrees Celsius. And we say to ourselves, uh-oh, that has to be in Kelvin. So we're going to convert that to Kelvin, and that is going to be 296. Kelvin. That's a temperature. It has an internal volume of 25 liters. You say, oh, our table's not long enough here. 25.0 liters. Okay, that's a volume. And the pressure is 3.18 atmospheres. We used up all the numbers. There's no second row of numbers. Well, that's okay. Let's just erase the second row. Like we planned it that way. Yeah, that's what we did. Most of life, actually, you end up just making up as you go along. I don't know if you figured that out yet or not, but You know, you look at people, oh man, they've got it all together. No, they're just better at bluffing than you are. So here we have now, we made this table, we realized, oh, maybe we didn't need it, but we've labeled all of our numbers. And we see that we have pressure, volume, temperature, and what are they asking for? Moles, that's N. So then we need an equation that has these variables. There's no 1s and 2s, so we don't want to use P1 over V1, or P1 V1 equals P2 V2, because we only have one pressure and one volume. So we want to use the ideal gas law, which is PV equals nRT. We're trying to find the number of moles. And we're trying to find moles, that's N. And so we're going to rearrange this equation to get N by itself. So we want N by itself, that means we need to divide by R and divide by T. Because R over R is 1 and T over T is 1. If we do it to one side, we have to do it to the other side. So now we have N equals PV over RT. With the ideal gas law, it's a good idea to check and make sure that your units on your quantities are the same as the units in the constant. So we've got temperature in Kelvin, volume in liters, pressure in atmosphere. So we're set. If, for instance, your pressure was in millimeters of mercury or torr or something else, it's generally more straightforward for students to convert that before you plug the numbers into the equation. So if it gave you 765 torr, convert it to atmospheres before you stick it in the equation, just like we did with the temperature. So then we just put these in. Pressure, 3.18 atmospheres. Volume, 25.0 liters. R, 0.08206. I know it's a pain, but put those units in there. Liter atmospheres per mole Kelvin. It's all together. And then the temperature was 296 Kelvin. Yeah, I run out of room all the time. 3.18 times 25.0 divided by 0.08206 divided by 296 equals 3.27. So N equals 3.27. I rounded to three significant figures because our volume and our pressure were given to us in three significant figures. When we converted the temperature to Kelvin, we ended up with three significant figures. And I'm going to double check my units. Atmospheres cancel, liters cancel, Kelvin cancels. The unit ends up being 1 over moles, which is the same as moles. It's just flipped upside down twice. So 3.27 moles. Any questions?
And where did you get the three significant figures from?
3.18 atmospheres has 3 sig figs. 25.0 liters has 3 sig figs. The 23 degrees Celsius looks like it has 2, and it does have 2. But when we add 273, 296 has 3 significant figures, because the rule for adding is different. And, you know, I give you multiple choice exams. The calculator says 3.2729841171. So there would not be a choice that was 3.27 and a choice that was 3.273 intending to trip you up based on number of sig figs. I don't do that in Chem 10. I would think about doing that in Chem 1. They deserve it. Well, depends. Depends on the, yeah. Because I could if I wanted to. Power. Any questions? So PivNert, PV equals nRT, has 4 variables. So they have to give you 3 of them, and you calculate the other. What about R? R is a constant. I'll give you the value of that constant for the exam. You don't have to memorize it, but you do have to think to go look for it. Okay, so R is a constant. I always get people ask me, where'd you get 0.08206 from? That's what R is. It's always the same. Here's another problem. What's the pressure in a 304.0 liter tank that contains 5.670 kilograms of helium at 25 degrees Celsius? So this one doesn't have nearly as many words. And we see we've got 3 numbers in there. And so we're probably thinking, well, we've got 3 different units. This is not going to be one of those named gas laws, Charles Boyle or Avogadro or any of those guys. So maybe we'll recognize on this one that we've got PV equals nRT going on here. And so the pressure, so you could make a table, and that would be fine. I'm just going to show you another way. You can say, okay, well, we've got 304.0 liters. Liter is a unit of volume, so that must be V. And the next number is 5.670 kilograms. You're like, yeah, I don't know what to do with that. I'm going to skip that one for now. Just leave it sitting there. 25 degrees Celsius, that's a temperature. But we need to convert that. I'm going to add 273. I'm going to end up with 298 Kelvin. And you're like, okay, that mass, that's a mass. Kilograms is a mass. And what are they asking? They're asking for the pressure. So the pressure is the question mark. Like, well, I need, I've got PV equals nRT. PV equals nRT. I want the pressure, so I need to divide by volume. My equation is pressure equals nRT over V. Okay, I've got T and I've got V. R is always the same. N. I don't have N. That mass must have something to do with the number of moles. Can we change a mass into number of moles? Sure we can. We just have to pull some stuff from a previous chapter. Okay, so it's helium. Okay, most of these gas equations, we don't have to know what it is because they all behave the same, but this is kilograms of helium. I want to get to moles. I know how to do grams to moles. So I need to go, here's my little path over here. I'm going to take kilograms and I'm going to convert to grams, and then I can convert to moles. So there's this little unit conversion molar mass problem kind of hidden in there. So I want grams from kilograms. What does kilo mean? It means 10 to the third. Kilo means 10 to the third, which is 1,000. It's a bad 3. Try that again. 3. Okay, so that's 1 times 10 to the third. So now I've gotten to grams. I need to get to moles. So moles on top and grams on the bottom. Helium is an element, and so we just look it up in the periodic table. 4.003 grams is 1 mole. 5.670 times 1EE3 divided by 4.003 equals. The mass had 4 significant figures, so I'm going to keep at least 4 significant figures. which would be 1416 moles. That's a lot of moles. But 5.767 kilograms of helium is a lot of helium. Okay, so now that is N. Now I've got all my numbers that I need. So P equals N, which is 1416 moles, times R, 0.08206 liter atmospheres per mole Kelvin, times 298 Kelvin, and that whole mass is going to be divided by the volume, 304.0 liters. Let's check our units. Kelvin cancels Kelvin, moles cancel moles, liters cancel liters. So the unit on our answer is going to be atmospheres. So we've got 1416 times 0.08206 times 298 divided by 304.0 equals, so I'm getting, how many sig figs should that answer have? 3, yeah. Because the temperature, 25, when we convert to Kelvin, we end up with 298 Kelvin, which has 3 sig figs. So 113.9035989 rounds up to 114 atmospheres. Did anybody else get that number? Yes? Okay. Because it's so easy to make a mistake. You should always punch it through twice, or have a friend punch it through. 114 atmospheres, that's a lot of pressure. But that's a lot of gas for the mass. It's not that big of a container. Any questions? The nice thing about PV equals nRT is it doesn't have any fractions in it. So when you go to rearrange it, it's not that hard to rearrange. But you should be able to solve for any variable in that equation. Oh, good. Another one. We get more examples in Chem 10 than in 3A. So here's another question. At what temperature in degrees Celsius does 121 milliliters of carbon dioxide at 27 degrees Celsius and 1.05 atmospheres occupy a volume of 293 milliliters at a pressure of 1.40 atmospheres? Anybody think there's an awful lot of stuff in there? There's a lot of numbers in there. But we can figure it out. So we say, that there's just a lot of numbers in there. Let's make a table. Even like with the first one, we didn't end up needing the table. It didn't really hurt anything. So let's make a table. So I'm going to make a long table. Maybe it'll be long enough this time. So 1 and 2, we'll ignore the question at first and just go with the numbers. So 121 milliliters